In describing motion, we're talking about what is called kinematics. That's motion without regard for force. When motion is described with forces, we're talking about dynamics. For here, we'll talk about kinematics. And in this lesson, we'll define the quantities distance, displacement, speed, velocity, and acceleration, and the relationships among them. Distance as used in physics is the same as distance in everyday language. How far something moves. It's measured in meters or some other length unit. Distance doesn't depend upon direction because it's a scalar quantity, which can be described by how much, not which direction. Here we see that Barry Biker has moved a distance d. Displacement is a little trickier. It's the straight line change in location between the starting and ending points of motion. Displacement is a vector quantity since it involves both a distance and a direction. Consider this top view of the path that Barry Biker rides in going from location A to location B. The dotted path shows the distance traveled. The vector shows the displacement traveled, a straight line path. For motion in a straight line, that's linear motion, we won't need to distinguish between distance and displacement. For practical purposes, they're the same. In my lessons, I prefer to use distance. Speed, how fast something moves. Speed is a measure of distance divided by time. Distance per time, like miles per hour or meters per second. The equation for speed is v, we use the symbol v for speed, is equal to distance divided by time, or in shorthand notation, d over t. When we talk about average speed, we're talking about the total distance covered in a particular time interval. So average speed is total distance covered per that time interval. In shorthand notation, v bar equals d over t. The bar over the v indicates average speed. What's your average speed if you walk 100 meters in 40 seconds, for example? We see that it's 100 meters per 40 seconds. That's 2.5 meters per second. That's your average speed. We can rearrange this equation and express it for distance. d equals average speed times time. Then we see that if you walk an average speed of 2.5 meters per second for 100 seconds, the distance you travel is 250 meters. Instantaneous speed, the speed at any instant. Whenever we take a trip, our speed at any instant may differ from our average speed. We likely speed up in places and slow down in others. Our instantaneous speed, our speed at any instant, is what a speedometer indicates. As we speed up from rest, our speedometer may read 10 miles per hour, then 20 miles per hour, etc. At the instant the speedometer reads 20 miles per hour, that is the instantaneous speed. Yum. Velocity. Speed with direction. Velocity is a vector quantity described by both magnitude, how fast, and direction, which way. We may have a velocity of 20 miles per hour east, then 20 miles per hour west in the opposite direction. In both cases, our speed is 20 miles per hour. When the velocity or speed changes at a steady rate, average velocity or average speed is simply the sum of the initial and the final speeds or velocities divided by 2. That is, it's average velocity, initial velocity plus final velocity divided by 2, where the bar over the v indicates average velocity, and v sub 0 the initial velocity, and v sub f the final velocity. Suppose Biker Barry rolls down a hill with his engines off, beginning at rest and reaching the bottom at 6 meters per second. What's his average speed on the hill? We see average speed is 0 meters per second plus 6 meters per second, the final speed, divided by 2. His average speed, or his average velocity, is 3 meters per second. Yum. That's simple enough, but remember, this equation is only for motion that changes at a steady rate. Distance traveled is found by multiplying the average speed by the time interval. For example, how long is the hill we just discussed if it takes 5 seconds for Barry's ride down the hill? We see it's average speed times time, 3 meters per second times 5 seconds. We see the hill is 15 meters long. Yum. Acceleration, the rate at which velocity changes. This is more difficult to comprehend than the other terms. Let's have a go at it. Our definition: A is change in velocity over some time interval, which we can say is delta V over delta T. Delta meaning change in. And that change in V is the final velocity minus the initial velocity, and that's all over the change in time. For the time being, we consider only constant acceleration, where velocity changes at a steady rate. The standard unit of acceleration is meters per second, or meters per second squared. As an example, if an object accelerates from 4 meters per second to 12 meters per second in 4 seconds, the acceleration would be A delta V over delta T, 12 meters per second minus 4 meters per second, all over 4 seconds. That's equal to 8 meters per second divided by 4 seconds. We get 2 meters per second over 1 second, which is 2 meters per second squared. That's the acceleration. In each second, the velocity changes by 2 meters per second, which is why we say the acceleration is 2 meters per second, or 2 meters per second squared. From the equation A is delta V over delta T, we can arrange that and get delta V equals acceleration times time, where delta T is just the time interval T. The equation says the change in velocity equals the acceleration multiplied by the time. And the change in velocity, delta V, is V sub f minus V sub 0, and that's equal to AT. Rearrange that and we get the final velocity equals the initial velocity plus the acceleration times the time. This equation says that the instantaneous velocity of an object at a time t equals its initial velocity plus AT, the additional velocity acquired due to acceleration during this time. It's used a lot, so we put it in a red box. There are 2 other equations that are useful in solving kinematic problems. This one, d equals v sub 0 t plus 1/2 at squared. This eliminates final velocity from the equation. Here's another one. 2 times acceleration times distance equals final velocity squared minus initial velocity squared. This equation eliminates time from the equation. We put these important equations in a green box. The equations we've discussed, interestingly, are not laws of physics, but are simply definitions and relationships expressed in mathematical notation. All equations are for motion along a straight line. In later lessons, we'll discuss curved motion. I want to leave you with a question. Suppose that Barry Biker, with his motor off, coasts down a hill from rest. He moves at a smooth, small, and constant acceleration. In 4 seconds, he reaches a speed bump while moving at 12 meters per second. What's the distance between his starting point and the speed bump he encounters? In short, how far does Barry travel in 4 seconds? Got that? Until next time, good energy.